if we have to prove that total resistance is equal to sum of the resistance of each resistor in series combination of resistor, then we can prove this way. Three resistors are shown to be connected with each other, maybe more than three. Resistance of each of the resistor is given here, R1, R2, R3. These are the resistance of three different resistors. We can use more than this also. And after the diagram, we can say that let the resistors having resistance R1, R2, R3, etc. are connected in series and PD across, and potential difference, I am writing shortly, PD across them are B1, B2, B3, etc. respectively. It means, let's say potential difference across this first resistor is B1, potential difference across second resistor is B2, and in the same way third resistor is B3, and their resistance is R1, R2 and R3. After this much representation, if we measure potential difference between these 2 points, let's say A and let's say this in B, if we measure the total potential difference, then what we get, we can write this way: practically the PD between A and B is found to be equal to the sum of the potential difference of V1, V2, V3, etc. Okay, practically, why I told this practically, potential difference between this A and B is, if let's say V, then this is found to be equal with V1 plus B2 plus B3 and so on. That's why I'm writing this way. PD between AB is taken as capital V. Okay, after this much saying, we can say that we can write that V equal to B1 plus B2 plus B3 plus so on. This is, let's say, equation number 1. Now, according to Ohm's law, all of we know that Ohm's law says that potential difference is the product of current and resistance. Let's say this is equation 1, and in the same way, potential difference across first resistor V1 is equal to, this is second because first is here, and V1 is equal to I R1. Why I am taking just I, and why R1? Because resistance of this resistor is R1, but the same current passes through each of the resistor. That's why value of current is I for same, but resistance of each of them is different. Okay, this is number 3. Okay, this is V2 potential difference against across second resistor is, if B2, then B2 equal to IR2. This is equation number 4, let's say, and B3 is IR3. This way we made few equations. Now what can say after this? Substituting the value of this b, b1, b2, b3 from this equation to equation number 1, what we get? I'm writing this, substituting the value of b, b1, b2, b3, b4, b2 and b3 from equation, there is no b4, from equation 2, 3, 4 and 5. In equation 1 we are substituting this value from this in equation 1. Then what we get, I'm writing here. Now what we get, B becomes IR. IR is equal to, B1 becomes IR1 and B2 is IR2, B3 is IR3 and so on. And if we take, we can see OR here, if we take I as common here, then we have R1 plus R2 plus R3 plus so on. Then I cancel. Therefore, R is equal to R1 plus R2 plus R3 plus so on. This way, we can prove what we proved. If resistors are connected in series, then the total resistance between two terminals of this conductor is equal to sum of the resistance of each of the resistor, and mathematically the total resistance R is equal to R1 plus R2 plus R3 plus R3. This can be used to solve numerical problems. Okay, this much for today.